Today we'll continue in section 8.8. When we finish that, we'll work on the worksheets from section 8.6 and 8.8. Tomorrow we'll have a test 3 review during class. And remember that on Friday is test 3. Okay, we got to this part. Simplify the square root of negative 500. So rewrite it as the square root of 500 times the square root of negative 1. We'll simplify the square root of 500 and replace the square root of negative 1 with I. The largest factor of 500 that's a perfect square is 100. 100 times 5 is 500. So we can rewrite this as the square root of 100 times the square root of 5 times I. And then the square root of 100 is 10. So our simplified answer is 10 times the square root of 5 times I on the outside of the square root. And one more, the square root of negative 99. First, write it as the square root of 99 times the square root of negative 1. The square root of 99 can be simplified. The largest factor of 99 that is a perfect square is 9. 9 times 11 is 99. So this is the square root of 9 times the square root of 11, and then replace the square root of negative 1 with I. And then the last step, the square root of 9 is 3, so we get 3 times the square root of 11 times I. Okay, so if you can remember that we use the definition I equals the square root of negative 1, and if you also remember how to simplify square roots, then simplifying square roots of negative numbers is pretty easy. Here's a little bit more information. If you go on to college algebra, you'll learn complex numbers at a higher level. But for now, I'll just mention the definition of a complex number. A complex number can be written in the form a plus b times I, where a and b are real numbers. The real part of a plus b times I is the real number a. And the imaginary part of a plus b times I is the real number b. And then here's a note. Every real number is a complex number whose imaginary part is 0. So for example, the real number 7 can be written as 7 plus 0 times I, where I is the square root of negative 1. So the thing to remember that will be useful if you take college algebra is that, I'm just reiterating what was stated above, every real number is a complex number but not every complex number is a real number. Okay, let's move on to the worksheet for section 8.6 and then the worksheet for section 8.8. The worksheet for section 8.6 has to do with solving the equations with radicals. A couple of the equations we've seen before, but we can go ahead and solve them anyway. To solve this equation, the square root of 4x minus 3 equals 7. Since the square root is isolated, we can begin by squaring both sides. So we square the square root of 4x minus 3. And we square the right-hand side. When we square the square root of 4x minus 3, we just get 4x minus 3. And when we square 7, we get 49. And now we have a pretty simple equation to solve for x. So add 3 to both sides, we get 4x equals 52. And then divide both sides by 4, we get x equals 13. Hey, this one's easy to check. In the original equation, replace x with 13. And it turns out to be a true statement. So x equals 13 is the solution. In part B, the square root of 6n plus 1 plus 4 equals 8. The first step in this one is subtract 4 from both sides. So we get the square root of 6n plus 1 equals 4. And now we can square both sides. To eliminate the square root, we square both sides. So the square root of 6n plus 1 squared equals 4 squared. And then on the left-hand side, when we square the square root of 6n plus 1, we get 6n plus 1. And 4 squared is 16. Then to solve for n, first subtract 1, we get 6n equals 15. And n equals 15 divided by 6, which simplifies to 5/2. And part C, what should we do to solve the cubed root of 11x plus 4 equals 5? We want to solve for x. We see that x is in the radical with index 3. So what do we do to start with?
Both sides by the third power.
Anybody online have an answer? Well, since we have the cubed root, the third root of 11x plus 4 equals 5, we want to raise both sides to the third power. So the third root of 11x plus 4 to the third power equals 5 to the third power. The cubed root of 11x plus 4 to the third is just 11x plus 4. And 5 to the third, 5 times 5 times 5 is 125. Then subtract 4 from both sides. We get 11x equals 121. And then divide both sides by 11. X equals 121 divided by 11. 121 divided by 11 is 11. Okay, so x equals 11 is the solution. Okay, in part D, what do we do to start? How do we solve this equation for v? What's the first step?
Subtract 10 from both sides.
So on line, what's the first step in part D? We want the square root of v minus 10 to be by itself. So we want to subtract this 10 from both sides first. So we get the square root of v minus 10 equals v minus 10. Well, we'll go through the process here in a minute, but let's just consider what we're looking at. The square root of v minus 10 equals v minus 10. So this is like noting that the square root of a number is the number itself. Can you think of any numbers whose square roots are just the number itself? Or are there any? Maybe sometimes we don't have solutions. Does there exist a number whose square root is the number? Yeah, I got an answer on line 1. The square root of 1 is 1. That's one possible, or that's one answer. Is that the only one?
0.
Yeah, 0, the square root of 0 is 0. So there are two numbers whose square roots are the number. But let's go through the process and see what we get when we solve this equation. Okay, so the square root of v minus 10 equals v minus 10. To get rid of the square root, we're going to square both sides. So we square the square root of v minus 10. And square the right-hand side. V minus 10 squared means the same thing as v minus 10 minus, or times v minus 10. When we square the square root of v minus 10, we just get v minus 10. When we square v minus 10, that is v minus 10 times v minus 10, we get v squared, and we get minus 10v minus 10v a second time for a total of minus 20v. And then negative 10 times negative 10 is positive 100. Okay, so now we'll make the left-hand side 0 by subtracting v and adding 10. So 0 equals v to the second minus 21v plus 110. Okay, can we solve this by factoring? It doesn't look like 0 is a solution. Oh. Well, 0 isn't a solution. We'll come back to that later. Let's see if we can solve this by factoring. So 1 times 110 is 110. Can we find two integers that have a product of 110 and add up to negative 21? Yeah, so negative 10 and negative 11 are two such numbers. Negative 10 times negative 11 is positive 110. And negative 10 plus negative 11 is negative 21. So the two factors turn out to be v minus 10 and v minus 11. So the solutions to this equation are v equals 10 and v equals 11. Okay, so it is true that the square root of 0 equals 0 and the square root of 1 equals 1. When v is 10, 10 minus 10 is 0. So when v is 10, we get the square root of 0 equals 0. And when v is 11, 11 minus 10 is 1. So the square root of 1 is equal to 1. It's just that v itself is either 10 or 11. Okay, the next problem, 12x minus 3 to the 1/4 equals 3. We want to solve for x. So what do we do first on this one? If we have something raised to the 1/4 power, that's equivalent to a radical with index 4. So we don't need to convert it to a radical, but you can if you want. But since it's 12x minus 3 to the 1/4, we want to raise both sides to the 4th power. So we get 12x minus 3 to the 1/4 raised to the 4th power, and then raise the right-hand side 3 to the 4th power also. So remember the property of exponents. We have 12x minus 3 to the 1/4, and that is raised to the 4. We multiply the exponents, 4 times 1/4. 4 times 1/4 is 1, so we just get 12x minus 3 to the 1st, which is just 12x minus 3. And then 3 to the 4th is 81. Then add 3 to both sides, we get 12x equals 84. And x is 84 divided by 12, which is 7. So x equals 7. And the next example, the cube root of 8y minus 5 plus 8 equals 3. The first thing to do is subtract 8 from both sides so that we isolate the cube root of 8y minus 5. And that's equal to negative 5. Since we want to solve for y and y is inside the radical with index 3, To eliminate the radical, we raise both sides to the third power. So the cube root of 8y minus 5 to the third equals the number negative 5 to the third. The cube root of 8y minus 5 to the third is 8y minus 5. And negative 5 to the third, negative 5 times negative 5 times negative 5 is negative 125. Then add 5 to both sides. We get 8y equals negative 120. And then divide both sides by 8. We get y equals negative 15. Okay, the next one, the square root of w plus 100 minus w equals negative 10. So first we add w to both sides, and we get the square root of w plus 100 equals w minus 10. Then we'll square both sides. Square the square root of w plus 100. And when we square w minus 10, that means multiply w minus 10 times w minus 10. On the left-hand side, when we square the square root of w plus 100, we get w plus 100. And on the right-hand side,
It's supposed to be plus 10. Oh,
yeah, so when we multiply w minus 10 times w minus 10, we get w to the second minus a total of 20w, and then plus 100. We'll make the left-hand side 0 by subtracting w and subtracting 100. So we get 0 equals w to the second minus 21w, and plus 0, because when we subtract 100 from both sides, we're just left with w to the second minus 21w equals 0. Okay, we can solve this equation by factoring. The first step in factoring is factor out the greatest common factor, which is w. So 0 equals w times w minus 21. This equation down here has two solutions, w equals 0 and w equals 21. But look at the original equation. When you test w equals 0, replace w with 0, we get the square root of 100, which is 10. 10 minus 0 equals negative 10 is false. Where did all my 10s go? Oh. So w equals 0 is not a solution. When we test 21, replace w with 21. So let's test that down here. So when W is 21, we have the square root of 21 plus 100 is the square root of 121. And then minus 21, does that equal negative 10? The square root of 121 is 11, so we get 11 minus 21 equals negative 10. That is true. So W equals 21 is the only solution to that one. Okay, this equation we saw yesterday, 5 times the square root of x equals x plus 6. So we can solve it again real quick. Square both sides. So 5 times the square root of x squared equals x minus 6 squared. So when you square something, it means to multiply that something by itself. So 5 times the square root of x times 5 times the square root of x equals x plus 6 times x plus 6. So on the left-hand side, 5 times 5 is 25. And the square root of x times the square root of x is the square root of x squared. Then on the right-hand side, x plus 6 times x plus 6 is x to the second plus 6x plus 6x a second time plus 36. On the left-hand side, we get 25x because the square root of x squared is x. On the right-hand side, x squared plus 12x plus 36. We'll make the left-hand side 0 and then solve by factoring. So subtract 25x from both sides. We get 0 equals x squared minus 13x plus 36. And the right-hand side factors pretty nicely. X minus 9 and x minus 4. So this equation has 2 solutions, x equals 9 and x equals 4. As we saw yesterday, when we test both 9 and 4 in the original equation, we get true equations. Okay, on the next page, let's look at the section 8.8 worksheet. Simplify the square roots of negative numbers. So the first one, the square root of negative 144. Okay, so this is the square root of 144 times the square root of negative 1. The square root of 144 simplifies to 12, and then we'll replace the square root of negative 1 with I, so we get 12i, 12 times I. The next one, part B, the square root of negative 9 plus the square root of 16. So we haven't done this yet, but it's not hard. The square root of negative 9 is the square root of 9 times the square root of negative 1. We're adding that to the square root of negative 16, which is the square root of 16 times the square root of negative 1. And the square root of 9 times the square root of negative 1 is 3 times I. And the square root of 16 times the square root of negative 1 is 4i. So these are like terms. 3i plus 4i is 7i. And the next one, the square root of negative 11 this is the square root of 11 times the square root of -1. The square root of 11 cannot be simplified any further, so we just write the square root of 11 times I. But make sure I is not inside the square root where the 11 is. Okay, so more of the same. The square root of -50. This is the square root of 50 times the square root of -1. The square root of 50 is the square root of 25 times the square root of 2. And then replace the square root of -1 with I. And then finally, we get 5 times the square root of 2 times I. All right, the next one, the square root of -45 minus the square root of -20. Okay, so the square root of -45, we'll rewrite that as the square root of 45 times the square root of -1, and then minus the square root of 20 times the square root of -1. The square root of 45 can be simplified. 9 times 5 is 45. So this is the square root of 9 times the square root of 5 times I. The square root of 20 can be simplified. Square root of 20 is the same as the square root of 4 times the square root of 5, and then times I. The square root of 9 times the square root of 5 times I is 3 times the square root of 5 times I. And then minus the square root of 4 times the square root of 5 times I is the same as minus 2 times the square root of 5 times I. And we can simplify further. Both of the numbers have the factor I, and they also have the square root of 5. So 3 times the square root of 5i minus 2 times the square root of 5i is 1 times the square root of 5i, or just the square root of 5 times I. Okay, the next one, the square root of -75 plus the square root of -12. So first write it as the square root of 75 times the square root of -1. And then rewrite the square root of -12 as the square root of 12 times the square root of -1. The square root of 75 can be simplified. 25 times 3 is 35. 25 is a perfect square, so we have the square root of 25 times the square root of 3 times I. The square root of 12 can be simplified, so we'll write that as the square root of 4 times the square root of 3 times I. And then the next step, the square root of 25 times the square root of 3 times I is 5 times the square root of 3 times I. And then the square root of 4 times the square root of 3 times I becomes 2 times the square root of 3 times I. Okay, the two terms that we're adding are like terms. They both have the factor I, and they both have the square root of 3. So they can be combined by adding, and we get a total of 7 times the square root of 3 times I. Okay, the next example, the square root of negative 27 plus the square root of negative 48. Okay, so the square root of negative 27 is equivalent to the square root of 27 times the square root of negative 1. We're adding that to the square root of negative 48, which is equivalent to the square root of 48 times the square root of negative 1. The square root of 27 can be simplified. The largest factor of 27 that's a perfect square is 9. 9 times 3 is 27. So we write the square root of 9 times the square root of 3 times I. The square root of 48 can be simplified. 16 times 3 is 48. So this is the square root of 16 times the square root of 3. And then replace the square root of negative 1 with I. Then in the next step, the square root of 9 times the square root of 3 times I simplifies to 3 times the square root of 3i. And then we're adding that to the square root of 16 times the square root of 3 times I, which simplifies to 4 times the square root of 3 times I. And the terms are like terms. They have the same radical, square root of 3, and also a factor of I. So when we add those up, we get a total of 7 times the square root of 3 times I. Okay, the next one won't take quite as long, the square root of negative 169. This is the square root of 169 times the square root of negative 1. And what's the next step? So what should I write next after the square root of 169 times the square root of negative 1? Okay, there's an answer. 13i, that's correct. The square root of 169 is 13. 169 is a perfect square. And then the square root of negative 1 is replaced with the letter I. So 13 times I. Okay, the next one, the square root of negative 100 minus the square root of negative 49. Okay, with a little practice, we can do some things without writing everything down in detail. So we can just think of the square root of negative 100 as the square root of 100 times the square root of negative 1. And the square root of 100 is 10, and the square root of negative 1 is I. So in other words, the square root of negative 100 simplifies to 10i. And we're subtracting the square root of negative 49. So we know that the square root of negative 49 is the square root of 49 times the square root of negative 1. But the square root of 49 is 7, and the square root of negative 1 is I. So 10i minus 7i, that can be simplified to 3i. Okay, the next one, we have a quotient. So something in the numerator and something in the denominator. In the numerator, we have the square root of negative 25. So that's the square root of 25 times the square root of negative 1. In the denominator, the square root of negative 64, that's equivalent to the square root of 64 and the square root of negative 1. In the numerator, the square root of 25 is 5. The square root of negative 1 is I. In the denominator, the square root of 64 is 8. And the square root of negative 1 is I. We can simplify further because both the numerator and denominator have a common factor of I. So our simplified answer is a real number, 5/8. Okay, well, that concludes the worksheet, but there are some other problems that we can look at. On the section 8.5 lecture notes, that's the one on division with radicals. So section 8.5, division with radicals. This is how far we got when we were working on that. So remember, when we have expressions with radicals in the denominator, we want to rationalize the denominator. In other words, we want to come up with an expression that is equivalent or equal to the one that we began with, but with no radical in the denominator. So at the moment, we have a radical with index 3 in the denominator. So I'll rewrite this expression. So we have the cubed root of 169y. Remember that 169 is 13 to the second. And then we have a factor of y on the inside. Okay, so when rationalizing denominators, we usually, if necessary, multiply by 1 in a particular form. So multiplying by 1 doesn't change the value of the expression. We're just changing the form so that the denominator no longer has a radical in it. So we investigate this denominator. We already have 13 to the second. After we multiply by 1, we want, in the denominator, we want the cubed root of perfect cubes. So we're going to have to multiply by 1 in the form, the cubed root of something divided by the cubed root of the same thing. But how do we determine what goes on the inside of those cubed roots? Okay, let's look at what we already have. We have 13 to the second inside this cube root. What would I have to multiply by 13 to the second to get a perfect cube? 13. That's right, 13. 13 to the second times 13 is 13 to the third, which is a perfect cube. So this radical will have to have, the form that 1 takes will have to have a factor of 13 in both of them. Then in the original denominator, we have the cube root of y. Remember, y is y to the first. So we ask, what would I have to multiply by y to the first to get a perfect cube? Yeah, I'd have to multiply that by y to the second. So inside this radical, we need a y to the second and y to the second in that one also. So we're just multiplying by 1. So we'll take it a couple more steps. So in the numerator, we get 5 times the cubed root of 13y to the second. In the denominator, the cubed root of 13 to the second times y to the first times the cubed root of 13 times y to the second is the cubed root of 13 to the third times y to the third. And now we can, in the next step, simplify the denominator, and the radical will be disappeared. We'll no longer have a radical in the denominator. So the numerator is already as simplified as it can be, 5 times the cubed root of 13y to the second. And in the denominator, the cubed root of 13 to the third is 13. And the cubed root of y to the third is y. Okay, let's try the next one. In this one, we have the fourth root of 3y divided by the fourth root of 5. So we want an expression that is equal or equivalent to this one, but without the fourth root in the denominator. So what form should 1 take when we multiply the fourth root of 3y divided by the fourth root of 5? What form should 1 take?
5 cubed.
Yeah, the fourth root of 5 to the third, or the fourth root of 5 cubed. The reason we're choosing the fourth root of 5 to the third is because the fourth root of 5 times the fourth root of 5 to the third is the fourth root of 5 to the fourth. But since 5 to the fourth is a perfect fourth power, the fourth root of 5 to the fourth will simplify to 5. Okay, let's take this a couple of steps. Take a couple of steps to get to the end result. So in the numerator, we have the fourth root of 3y, and then the fourth root of 5 to the third, we want to simplify 5 to the third to 125. 5 times 5 times 5 is 125. And then in the denominator, we have the fourth root of 5 times 5 to the third, which is 5 to the fourth. Okay, then in the next step, we can write the simplified form. In the numerator, the fourth root of 3y times the fourth root of 125 is the fourth root of 375y, because 3y times 125 is 375y. And in the denominator, the fourth root of 5 to the fourth is 5. So we rationalize the denominator. meaning that the denominator is now a rational number. In other words, there's no longer a radical in the denominator. Okay, we're out of time. Go ahead and sign in for attendance.
Have a good day.
You too.